Hey everyone! Today we're going to finish up our lesson introducing acids and bases. In the previous lesson, we defined what an acid and a base is. We also learned how to find conjugate acids and conjugate bases and what the product's going to be. So in this slide, we're going to kind of review a lot of those topics that we talked about in the last lesson, and we're going to specifically write equations for a proton transfer reaction. Here it says the hydrogen sulfide ion, which is HSO3 with a -1 charge, is amphiprotic. Let's kind of review what amphiprotic is again. Amphiprotic, the prefix amphi, like amphibian, means both. It can be both an acid and a base, just like an amphibian can live in both water and on land. So we're going to write an equation for the reaction of this hydrogen sulfide ion reacting with water. So here it says in part A, we're going to write this as if it acts as an acid, and part B, we're going to write as it acts as a base. So we still have this hydrogen sulfide, and it's going to react with water. And down here, it's going to do the same thing. What we need to decide are what are the products going to be. So in part A, it's asking us to write this as if the hydrogen sulfide ion acts as an acid. Let's kind of go and review what does it mean to be an acid. In order to be an acid, this means you're going to be a proton donor. Means you're essentially going to donate a hydrogen ion. So what happens is one of these hydrogens, and there's only one, off this ion is going to be given to water. So I'm going to subtract a hydrogen, SO3, and that's going to affect the charge as well. I've lost a positive hydrogen, which means this is going to become more negative. So -1 minus 1 gives me a -2. That hydrogen went over to water. So if I was going to write H2O as a product, instead of having 2 hydrogen, it has gained a hydrogen. So it becomes H3O. Notice that this is neutral over here, but I have gained a positive charge, so this gives me a +1 charge. Now, what happens if this same ion acts as a base? Well, let's review what a base is. A base is going to be a proton acceptor, which means it's going to take the hydrogen. So here, if I'm looking at HSO3 -1, it's going to strip one of these hydrogens away from water. So instead of having 1 hydrogen, this compound's going to have 2. So H2SO3. Notice my charge over here is -1, but it gained a positive, so -1 plus 1. My charge is neutral, so nothing's written. Then I have to work on water. Well, water gave up one of its hydrogens. So when it gave up one of its hydrogens, most people are going to write that as HO. But now that we know our polyatomics, I'm just going to rewrite it as OH. Over here, it was neutral, but it lost a hydrogen. So I've lost that positive charge, so I've become a little bit more negative. So there's my -1. Down below, it says in both cases, identify the conjugate acid-base pair. So if I'm looking at this, in this case, I had an acid, which means my water acted as a base. My acid, whatever structure that is, it becomes SO3 -2. This must be my conjugate base. My water, which was originally a base, will become my conjugate acid. If I look in part B, my ion acted as a base. That means water acted as an acid in this instance. Now I have to figure out who is my conjugate acid base. Well, if hydrogen sulfide was a base, that means sulfurous acid, which is H2SO3, is going to be my acid, my conjugate acid, and my water becoming hydroxide, this is my conjugate base. Let's try this and give another example. It says with lithium oxide is dissolved in water, the solution turns basic from the reaction of oxide ions with water. So this is a reaction between O with a 2 negative reacting with water, so H2O. And we're going to write an equation for this reaction and identify the conjugate acid-base pairs. Well, if I'm looking between these two molecules, you might ask yourself, who is an acid and who is a base? Well, acids have to donate a hydrogen. Oxide ions don't have a hydrogen to donate. So this can't donate, it can't be an acid, which means this is most likely a base. So I'm going to put B for base, and my H2O is going to have to be my acid. So since water is now my acid, I have to say water is going to donate a hydrogen. So if it donates a hydrogen, this O2 negative is going to get an H. So OH. Here I have a -2 charge and I've gained a positive, so that's going to become -1. And if I look over here on water, water gave up one of its hydrogens, so now it's just OH. And then since it was neutral, it lost a positive, it becomes a -1. So here I have two hydroxides, so you can label either one of these, conjugate acid and conjugate base. Now, some acids are better proton donors than others, and some bases are better proton acceptors than other bases. And so this is where we look at strengths of our acids and bases. In other words, the more easily a substance gives up a proton, the less easily the conjugate base is going to be able to accept a proton, and vice versa. So one thing to note is that the stronger the acid, the weaker the conjugate base. Or you could say the stronger the base, the weaker the conjugate acid. There is an inverse relationship between an acid and its conjugate base. So if I'm looking at this, one, a strong acid, if it completely transfers its protons to water, which means it leaves no undissociated molecules, your conjugate base is going to be negligible. And negligible just means it's so small it's hard to read. If I have a weak acid, it only partially dissociates or splits in a solution, and therefore its conjugate is going to be a weak base. And then if a substance has negligible acidity, which means it barely has any acid to it, the hydrogen is not going to dissociate, and so you are going to have a strong base. This is the scale that we use. Notice that here I have strong acids and it's across from a very, very weak, negligible base. Here, weak acids, weak bases. And then over here, if I have such a small acidity, I have a very strong base. So in every acid-base reaction, equilibrium is going to favor the transfer of the proton from a stronger acid to the stronger base in order to form weaker acids and weaker bases. So in this question, and you're going to see something similar to this on your homework, it says 1, label the following acids as strong, weak, or negligible. So let's go through and look at these. Note, this problem says that they are all going to be acids. So I want to look on the acid side of the chart. I need to figure out if they're strong, weak, or negligible. So here, H2PO4 -1. So I need to look on my acid side. And if I look, here I have H2PO4 -1, and it's in the weak acid range. So this is a weak acid. If I look at HF and I look down below, HF falls within the weak acid range. So we're going to say that this is a weak acid. Now I'm going to look for H2SO4. I find H2SO4, I'm going to notice it up here. This is in the strong acid range, H2SO4. And then NH4 plus, if I look down at my chart, I'm trying to find NH4 plus. You're going to see right here, it's in your weak acids. So I'm going to classify that as a weak acid. Then step number 2 says, I want to write the conjugate base, which means, remember, acids donate H pluses, or basically protons. So if I'm going to write the conjugate base for this, I need to donate a H plus, so I'm going to lose a hydrogen, so HPO4. And if I'm losing a negative charge, I'm going to become more, or losing a positive charge, I'm becoming more negative. So HPO4 negative 2. Over here, I'm losing my hydrogen, so I have no hydrogen. I went from neutral to losing, so negative 1. Here, if I have H2SO4, I'm losing a hydrogen. I get 1 hydrogen, SO4. And since I went from 0, a neutral charge, to losing 1, I get a negative 1. And then over here, I have NH4 plus. I'm going to lose a hydrogen, so NH3. I was a plus 1, but I lost 1, so that gives me a neutral or no charge. Then step 3 says, I need to label this conjugate base that I just created as either strong, weak, or negligible. So what I'm going to do is, since this is a conjugate base, I need to look at the base side. So I need to find HPO4 negative 2. So I'm going to look over here at the base side, HPO4 negative 2. Notice right here, it's going to be right across from the H2PO4 because these are conjugate acid-base pairs. So this, notice it's in the weak base section. So weak base. If you're looking over here for your F negative 1, you're going to see that you're going to look in the base pair. So you have an F negative 1 in the base side, so you're going to see that that is a weak base. And then if you look at for HSO4 negative 1, HSO4 negative 1, you're going to see it up here. This says that it's under negligible acidity. Oops. So negligible. And then if I look for NH3 on the base side, if I look for NH3, notice it's right here. I have a weak base. Oops, weak base. So notice a weak acid is with a weak base. A strong acid is with a negligible base. Okay. Now let's try this same example problem. It's going to work the same way, but instead of giving acids, we are originally going to give you bases. So you're going to have to look at these bases and label them as strong, weak, or negligible. So here I'm going to look for chlorine up on my table above. Notice it says it has a negligible. So this is negligible basic solution. Then I'm going to look for PO4 3 negative. If I look over here, PO4 3 negative, that puts me at the weak base category. Oops. Next, I'm going to look down here, HCO3 negative 1. HCO3 negative 1 gives me a weak base. And then if you look over here, CH3 negative 1, so I'm going to look back at my chart. If I find CH3 negative 1, CH3 negative 1 is in my strong base section. So this is a strong base. Then part 2 says write the conjugate acid. So remember, if I'm a base and trying to write an acid, bases are going to accept protons or accept an H plus. So instead of Cl negative 1, I'm going to gain a hydrogen. So HCl, I'm gaining a positive charge, so this negative 1 becomes neutral. If I'm looking at phosphate, if I gain a hydrogen, HPO4, I'm gaining a positive charge, so this goes to be a negative 2 because I'm becoming more positive. If I look at HCO3 negative 1, I'm gaining a hydrogen, but I already have a hydrogen here, so I'm going to write it as 2 hydrogen, CO3. I have a -1, but I've gained 1, so I have no charge. And then here I have CH3, -1. Well, my hydrogen, I originally had 3, but I'm going to gain 1, so that's 4. And since I'm gaining 1, there's no charge up here, so CH4. Then for part 3, we need to label the conjugate acids. So all of these that we wrote are acids. So we're going to look at that acid side and say if it's strong, weak, or negligible. So I'm going to find that HCl. If we look at the acid side, HCl right here is under strong acids. So I'm going to say that the conjugate acid is a strong acid. Notice negligible base becomes a strong acid. Here, weak base. Now, if we remember the kind of rule for this, this should be a weak acid. Let's go ahead and check. HPO4. HPO4 2 negative right here. And that is a weak acid. We are correct. Here we have H2CO3. So I'm going to look over on the acid side. H2CO3 right here. That's a weak acid. And then over here, I have CH4. Now note that this was a strong base. So think about the little tips and tricks we've learned. CH4 is going to be the opposite. So instead of being a strong acid, we look up at our chart, CH4 is actually a negligible acid. So neg acid. And that's the end of today's lesson. If you have any questions, just make sure you shoot me an email or come up and ask. And I hope you guys have a great day.